meteorite impact, catastrophic events in the astroplasm.
Thank you. Thank you for inviting me here. I will discuss all meteorite impacts, catastrophic events and astrobiology together with my students. And I have to say, looking at these last two talks, the talk that I will give is a very simple review and mainly focusing on the impacts. I try to bind this talk into astrobiology, but I'm not really doing astrobiology, but we have started to think about a little bit these consequences. Yes. Okay. In Helsinki University where we are working, we are looking at the astrobiology concept in a little bit different way perhaps. We don't only look at the impacts, but we look at several phenomena which can be bind into, perhaps into potential biological consequences. We are looking at the Earth's magnetic field and its effect to protecting the cosmic rays, and that has a meaning for astrobiology. We are looking at tectonics, we are looking at supercontinents in ancient time and the consequences for evolving life on Earth mainly. We are looking on meteorites which have potential to perhaps bring life onto the Earth. And in particular we are looking at impact structures, mainly terrestrial impact structures, and focusing a lot to Fennoscandia, like you will see. So what type of cosmic materials arrive to Earth, at least from our point of view? We are looking at the cosmic dust, or interplanetary dust, or micrometeorites. We are looking at meteorites itself, all types, and the impacting bodies, whether large meteorites, whether asteroids, or whether cometary pieces. And of course there are also space junk, which is a new one we will discuss here. So if you look at our solar system and the terrestrial bodies, we can say that the impact cratering is really a ubiquitous process in the solar system. You only have to look Moon, very similar to Mercury, also Mars, and so on. However, if you look at the Earth, it's very different for several reasons. Earth is strongly a dynamic planet, where plate tectonics is ongoing, erosion is ongoing, volcanism is ongoing, which is mainly destroying the impact record. However, we have impact record on Earth, but we will look. Before I go to the Earth, just to remind you some of the, well, let's say recent impacts. Many of the geological people or geological community say that impact is a sort of past event, it doesn't happen anymore. You only have to go back some 10 years, by the way, 10 years. when we saw by our naked eyes almost impacting in Jupiter, the Shoemaker levy. And there are several cases, what I call close encounters, where Tunguska is the famous one, which did not produce an impact, but it produced an explosion. There's another fast flight, and there are several cases of these, let's say, close encounters. So why we look impact craters, at least from our point of view? They provide geological evolution for the region or for the Earth. And very often in Finland, they provide the only geological evidence, because impact structures are protecting some of the sediments which once were here. You can see them, let's say, in Scandinavia. You can see the sediments in Estonia, but you don't see them in Finland. But we find them in impact structures. They are economically valuable, and for this talk in particular, they have caused environmental changes. Moreover, they provide knowledge for the shock processes. It's a natural way to look at the shocked rocks and shock processes, which then can be compared to laboratory studies. And they also may give information on the projectile hitting on Earth. So how we recognize the impacts? I will show examples, so I'll only list here the main titles. You have to look in combination. You have to look the mineralogy of the shocked rocks. You have to look the impact rocks, which is the lithological point of view. Geochemistry is very important. Geophysics important, and also morphological point of view. When you combine these, let's say, recognizing evidences for impact, you can perhaps say that we have a confirmed impact case rather than just a suspect. And the indicators, here are examples from several impact structures. For example, we have in Lappajärvi, you will see later in Finland, one of the 11th impact structures. We have impact diamonds, so not terrestrial diamonds, well, not mantle diamonds, but impact diamonds. Then we have lithological impact breccias, which are highly brecciated rocks, shatter cones, which are produced also by high shock pressures. This is from Sudbury, Canada, very nice shatter cones. Here is another shatter cone, Martti Lehtinen here, another shatter cone from one of the Finnish structures, Suvasvesi. And if you look at the mineralogical point of view, you will see shocked deformations in quartz, shock lamella in quartz, several sets actually of the shock lamellas. All of these which are not produced by ordinary processes, you need really high pressures. Okay, if you look at the global record in the left, we have today about 175 impact structures or confirmed which fulfill these criteria on Earth. And we have some 32 in Fennoscandia and 11 in Finland. I don't go into statistics and so on. The concentration is in old Precambrian shields, Canada, Fennoscandia, Australia, and on where you carry out the studies, oceanic, perhaps only one really oceanic, and so on. But I don't go into the statistics. I might mention that if you look per area, if you normalize the impact structures per area, Finland has 11, Estonia a little bit less, but this area is the most, we have found most of the density of impact structure is the highest in the world. And this is perhaps a lot because we are focusing the studies in this area. And I might also mention that 7 of the impact structures were found during the last 10 years when we started the program. Simply, or at least one of the reasons is that we knew what we are looking for. But that, if you look this along list, if you look at the current status, we have some 175, and perhaps 5 new are discovered per year. The sizes range up to 300 kilometers. Oldest one is 2,300 million years old. And the shapes are typical bowl shape, complex, multi-ring, and doubles. There are not really, maybe there is one case, but there are not really impact chains on Earth found. The target rock is continent, crystalline or sediment, maybe oceanic, maybe there is one case, an oceanic. Several cases of shallow sea, not really on impact structures, as far as I know, found on an icy area in Antarctica or in Greenland. Okay, recognition was the shock features, geophysics, and several others. One very important geological is that the event is extremely rapid. We are discussing those seconds or 20 minutes compared to the geological timescales, which are millions of years. The event can be catastrophic and unlike typical geological process. I call it drawback, even though it's the main line of this meeting perhaps. But impacts are causing and can cause regional to global catastrophes. And several questions, but I come back in the last slide. Okay, I should compare with other planets, but I will skip it because I already said that the terrestrial, if you look at the cumulative number, the terrestrial record, which is the curve over here, does not follow the Moon, Mercury, and so on, because of the destruction of the smaller structures in time, and so on. There are several reasons why it differs in the earthquake. Examples are here, some examples. Lappajärvi is the most famous Finnish one, 23 kilometers, 73 million years old. This is a new age. These are the smaller ones, Arizona, well, everyone knows this one. Wolf Creek in Australia and New Quebec in Canada. And there are several cases of this small bowl shape, generally bowl shape without central uplift. Rim still existing, and so on. Larger ones, these are the more important ones. Poppy Guy in Siberia, about 100, this is it's 100 kilometers. Also the age is in error, 35 million years. In northern Siberia, very interesting impact structure, where the impact diamonds were originally discovered by Victor Masaitis. Six Group is the most famous one. Okay, these are the readings. For Six Group, 180 people are discussing or disputing the size. 180 is quite close, I think so. You can see it in remote sensing part on continent, the rest on the ocean part. This is the 65 million. This is the KT boundary impact event, which is most, at least, a very good candidate for the KT biological destruction.
The same for Poppy got out, but maybe anything also? KT boundary?
No, it's 35, so we are looking at the Eocene, Paleocene boundary. Possibility for the 35 border. That is a very good candidate for this one, but it has not been confirmed in what they as the 6 group for KT. But we are looking at it. So this should be 35. Suddenly Canada 180, notice pre-Cambrian 1850 million years old. This is the SAR image, remote sensing image. Notice it's deformed already because of the geological processes after the impact. And Bredeford, this is a geophysical map, gravity and magnetic data of Bredeford, South Africa, also a large one. Little bit older than the Canadian. Sudbury, but we are also looking, the age has been recently confirmed by several methods. Some of the geophysical data, particularly in Finland, we are using geophysics to identify and find impact structures, and we have found using geophysics impact structures. This is Sääksjärvi, Finland, gravity data. The Sääksjärvi, I don't have Sääksjärvi lake itself here, but it's kind of elliptical lake. But when you look at the gravity data, you can see a beautiful circular feature with perhaps other features also here, so the extent can be much larger. Here is the Söderfjärden in the Finnish coast, close to Vaasa. Again, aeromagnetics and topography combined. You can see very nicely the impact structure, which is old, Cambrian to pre-Cambrian boundary, 5 kilometers diameter. This is not bathymetry, it's wrong here. This is electromagnetics of a small impact structure we found some 5 years ago in Karikkoselkä using electromagnetics and gravity magnetics. Perhaps 230 million years old. And Siljan in Sweden, which is the largest in Europe, 55 kilometers and 360 million years old in remote sensing data.
So what is bathymetry? What is bathymetry?
Oh, bathymetry is the lake depth or water depth. But this is wrong. It's not bathymetry. The map is electromagnetics. I'm sorry, I have an error here. I have an example of bathymetry, but it came into wrong figure. Maybe it comes. Yeah, okay. Here you see that it's the same here. Okay, magnetics, two examples. Here we have a case in Finland where we probably have a doublet. We have the Suvasvesi Lake north, Suvasvesi Lake south, and we are discussing a lot whether this could be a doublet. Notice magnetic data or aeromagnetic data. Notice the very tiny central anomaly here, which was the point to go for drilling. And the drilling, they look something else, they look kimberlite pipes. The drilling went into directly impact melt sheet, which is producing this magnetic anomaly. And here you see, we don't have a central anomaly, but if you look, we have a weak, flattened magnetic relief, most likely destroyed by the impact. Some other cases, seismic data in Barents Sea. This is a shallow sea infrastructure found by seismic data by the Norwegians, near. And we are now working in Africa, in Bosumpi structure in Ghana. And this map is kalium content of the rocks. And there's a lake, so no data here is because we have a lake. But you can see that the kalium content enhanced by the impact produces the ring and perhaps second ring facing here. The fly lines are missing here, so but we are pretty sure we have a second ring.
What is the scale?
The scale is 10 kilometers. Oh, yes, good. 10 kilometers here, 2 kilometers here, 5 kilometers here, and some 20 kilometers here.
Why would you enhance the kalium?
I can't hear you.
Why would an impact enhance the kalium?
Oh, it's a granitic rock which has a kalium content, and that's a good point because we are not sure, but we feel that the hydrothermal events of the impact have enhanced the mobility of the kalium because of fluids. Topography is another possibility, but we don't know it exactly. But that was a surprise when we did the aerophysical flight. We used magnetics, electromagnetics, and because they have radiometrics, so I sort of said that keep that also running. And it was the radiometrics, the gallium content, which turned out to be the best data for this garment flight. Okay. Impact itself as a physical process, if we start from left to here, as I said, geologically, it's very rapid, so I put the second, or the time here, impacting projectile is coming, so 0.01 seconds, one second here, 1 minute here, and this is an example of the exact area, which is 560 meters, when you make the erosion, so that I don't look this one now, let's look only these. So it's a very rapid process where the projectile is making the cavity, ejecta is flying up, sometimes far away, and a lot of the ejecta is falling back and filling the once produced bone or cavity, making the impact ice to settle down in this side. There's another one, but I have personally looked very much, is the effects for the atmosphere and so on, or up to the stratosphere, which relates to this discussion here. When we look, we have to remember that in impacts we really look extremely high shock and temperatures. So here is temperature, pressure. Here are the geological temperatures and pressures. When we go to impacts, we are several orders of magnitude higher pressure. These are the features of rocks and minerals that we are looking. The same applies to the energy diagram. You can look even joules are active here, a unit which is not very nice unit, but nevertheless a Hiroshima unit, making some conversions. So here we look typically energy and frequency of events, geological data somewhere here, earthquakes we start to be here, and then we come slowly to the impacts. So higher energy, less often of course. Here I put Pasterka, it's a Finnish impact structure, 23 kilometers. And here is the KT, 6 energy and frequency. So here, this is really the impact energy calculated. This we don't go into details, but the impact itself is rapid. It has several effects on ecosystem. It can produce total melting, it can produce tsunami waves, earthquakes, and so on, maybe wildfires and darkness and acid rain and so on. But it's very complex cooperation, but in details I don't go. Chicxulub is a good candidate for the 65 million years impact. We are looking, the drilling is now ongoing, and we got some of the cores to Finland also. We are looking at impact melt and trying to estimate, redate, estimate the size, and also looking the effects to ecosystem, because the sediments are carbon containing and sulfur containing. There has been a lot of discussion whether impact correlates with some of the mass extinctions like the KT. And we are also doing this one. I would say that I looked also this one, and I have to say that there is no one-to-one correlation. Maybe the 65 can be a case to Chicxulub, but notice that there is also volcanism ongoing. There are mass extinctions which do not necessarily have an impact. So the system is not by no means a one-to-one correlation. We have to look and get better, particularly the impact frequency. I'll skip this one. I will finally look at the Fennoscandia, because we are also looking whether we have larger structures in Fennoscandia. Remember, Siljan was 55 in Sweden, Lappajärvi here was 23 and so on. And we have several cases where we see geophysical anomalies, but we are now looking. But I have to say that none of these has been yet confirmed to be an impact structure. There are hints, but none has not yet been. In Precambrian it's difficult to verify that. I'm also looking in another way, I'm looking what is called old mantle domes in Finland. And if you look, for example, gravity data in Finland, you can see that the old domes come up very nicely in gravity data. But this does not yet prove that they are impact structures. They can be geologically domed structures. But these are the ones that I'm looking as a potential at least. I said that we discovered some 7 during the last 10 years. The latest discovery in Finland is from this year actually. Satu Hietala and Jarmo Moilanen discovered a new impact structure, Keulusselkä called, and we are now working with geophysical data and dating of this structure. There is no doubt that it is not an impact structure. Beautiful shatter cones in Boulder, and also you can see shatter cones here on a road outcrop in situ. So it's a very nice case. We also have aeromagnetic data. We have a very nice aeromagnetic anomaly, even though it has some problems because the structures or the shatter cones are a little bit off. So we have to look whether they are correlating with it. Probably. Finally, I added here some questions. Some are very elementary, you are familiar with them, but nevertheless, the consequences of large impacts is missing here on planetary evolution. A lot of work has been done, including Fennoscandia. And what are the geological and biological effects of impacts, not only on land, ocean, ice. Can asteroids or meteorites bring life to planets? I'm looking particularly at the carbonaceous meteorites here. Did moon originate by impact? Most likely, but there is a lot of discussion here. And important for evolution is also have the planetary atmosphere altered by impact. And is there a periodicity in impact record? If there is, does it match with the mass extinction periodicity, which is roughly 30 billion years? The role of impact in early Earth during the heavy bombardment from 4,500 to maybe 3,900. And if you look at Archaea, the oldest rocks in the Earth, they have found a lot of these tiny spherules. Are they really impact ejecta layers or what they are? And okay, of course, for future, but I'm not doing that. What is the role of the NEOs to look future impacts and predictions and so on? And finally, at least for our group, the role of impact gathering in teaching must be taken into account. I might mention here that some 5 years ago, one of the famous textbooks in geology, geology textbook, did not even have word impact in the glossary. Thank you very much.
Any questions or comments?
So the recent claim of detection of the Permian Triassic crater in Australia, any comments on that?
Yes, I'm a little bit skeptic. I'm reading the paper of one of the reviewers, so I'm a little bit skeptic because they are a little bit, how to say, not very precise data. So it's tempting to look at that as a that way, but I'm a little bit skeptical myself.
Is there any kind of temporal connection between this KT extinction impact and then these big lava fields in India? Yeah.
The timing is the main connection. But that's a good point, because the timing of the decans or the dating of the decans is also changing. New data are coming in, they are a little bit changing, so I'm not sure whether they match anymore. 65.04 as the impact is now very precise. But nevertheless, the Deccan period was probably geologically not long, but nevertheless lasting a few million years. So these two have been acting together. So that should be also counted.
But can it be that really this impact, is there any kind of
calculations
that
Okay, I have not seen.
There are similar phenomena of Mercury on Mars, the Hellas impact on Mars and the calories on Mercury that definitely shows effects on the antipodes. The 6 lupus is too small for that. And also the latest datings of the Deccan, there are some, not the iridium data, but the osmium data, where you see a definite slope and then a peak in the middle.
Yes.
So that indicates that the Deccans perhaps started before the 6 lupus.
There are some hypotheses that in the early Earth, very heavy impacts could have erased the whole atmosphere, evaporized the oceans, because the gyres we had already some discussion about that. I would like to know what's your opinion, whether that can happen with a very big impact.
Theoretically, definitely, yes. I think I added that into the list, but I have to say I have not really.
All of impacted early Earth, you haven't shipped that.
I'm here also.
Yeah.
Yes, but I have not looked myself. But I know that the discussion is ongoing, so that's why I listed it.
What about the Santorini, Tira Island crater? Is it a volcanic blast off or an impact crater? What is the present concept?
I don't know. I think volcanic is the more favored, because there are not impact evidences in that way as for volcanic evidences. But again, I have not really followed last couple of years the Santorini question. I think volcanic is favored.
It's a huge volcanic.
Yes.
20 kilometers.
It's a kind of explosion of caldera. But for impact, you have to find the impact evidences, the diagnostic for impact, and I'm not sure whether Santorini has that. It has a volcanic evidences.
I was quite surprised by the clean pattern you saw in the gravity data for one of the impacts. Is that a general feature, and is it actually due to the deposits from the meteor, or what causes actually this pattern in the gravity data?
Stop me when you see that.
It was one of the other pictures where the impact was in blue, I remember.
Yeah, I think I know.
Much earlier, maybe. Maybe that one? No. Yeah, that one, right, maybe.
This is gravity.
Okay, that's the one, yes. Right.
Okay, this is exactly. This is a very typical gravity data for this size of impact, which means a central pole of gravity, because the rocks are less dense, they are fractured and less dense. Then you have this kind of enhanced, perhaps, pattern in gravity, which is typical. There is a tiny high before you go to the bone. And notice that, in particular, the gravity so strikingly this is typical, strikingly circular data for most of the impacts. Even though the morphology itself is often elliptical or disturbed, the gravity source integrates the deeper part of the impact, so that even if you have a shallow angle impact, the impact structure will be circular, unless you go less than, let's say, 15 or 10 degrees angle.
And the gravity perturbation in depth is relatively shallow?
Yeah, it's relatively shallow, yes.
What's the amplitude, relative amplitude of that?
This was about, if I say minus 6 milligauss, that would be close. I don't have the scale now here. But it's typical, it's also typical for this diameter, yes. It could be minus 6 milligauss.
Gauss.
Milligauss, yeah. Milligauss.
Gallon.
Gallons. Yeah, comes from Galileo.
Aha. Wow. Okay.
Look here, units. Milligauss.
Nice.
Is it possible to that is there any evidence for the said impact that created the moon? Whether the effect crater during that can survive the Earth activity? Is there any evidence for that kind of thing? We have the theoretical kind of things. Is there any observational evidence for the impact rate kind of the thing? Is there any remnant which you can see that there was further impact created on the Earth?
You mean on Earth?
Yeah.
I doubt. But if you look at compositional data, the Earth, I think it can be explained in that way. There is no big dilemmas in the compositional data. So it's a very likely possibility which is now re-raised again into question.
So you showed that the size distribution of the different impacts in the same diagram as the earthquakes. It looks like the scaling law, and it looks like it has almost the same slope as the size distribution of the earthquakes. Is that an established fact, or?
Yes, for the larger diameters, yes. Yes. And also, if you calculate the rate, even though we have this 175 infrastructures on the Earth, if you calculate that for the area where they are discovered, the rate is matching for a reasonable level for observed asteroidal data.
What's the status for?
-2, I think it was used here. But people are using -1 point something and -2 point something. But this was -2.
Right, so you mentioned this huge physical effects at very high temperature at the moment of impact, so in the surrounding. But now I would wonder of what are the physical conditions within the core of the safe comet, for instance, when it comes in. And this relates to now some earlier discussion of whether there would be organic molecules or even organisms inside. So I realize that very small micrometeorites have come down very smoothly, nicely, but how about big ones? Would you have any endurable conditions in the middle?
I think I lost your question. I'm close, but I lost your question.
Okay, sorry. So very hot and very high pressure on the impact the surface, both on Earth and in the project factor. But would you have any endurable conditions in the middle of the project factor?
Okay,
Inside.
yes. To answer your point correctly, that the pressure into the, we are looking the pressure into the target loss, but we also should look the pressure into the projectile
Yeah,
itself.
it's in very nice conditions anywhere.
No.
But it is big enough that it stays cool inside.
Now it disappears.
The projectile fuses away. It will be, the temperature goes up to 10,000, even higher, 10,000 degrees, pressures are extremely, so you don't see the projectile anymore. You see a fingerprint of the projectile. For example, iridium, which is quite stable in this way, will contaminate the target.
Is there any size of objects?
Small ones.
Small ones, yes.
Small ones. Tons and tons.
But yes, very microscopic.
No. Also meteorites are found, I mean, not big ones, but meteorites are found from close to Arizona, they are found in Estonia. But not big ones. Just tiny fragments. Larger than the dust particles, but sizable meteorites.
In this case, 100 ton is a fragment.
Okay. It's a fragment.
100 tons, yes. I mean, they found on Greenland parent brought back to New York, and we have in Copenhagen several iron meteorites, but that's iron.
Yes.
And the living conditions in the middle of iron.
And there is another point, of course, that the meteorites themselves, they penetrate the atmosphere, but finally they usually land in a as a free-falling body. Whereas those which are really keeping the kinetic energy, they come with the hypervelocity, with the cosmic velocity, 25 to whatever, 70 kilometers per second. So the atmosphere does not slow them down as ordinary meteorites. That's why the meteorites does not make impact, they make a tiny.
Just a small comment. There is one useful number to know that there is a limit in the size distribution. So if particles less than around 50 microns in size, then it comes down without being changed at all. So it comes completely even. And then you have all these intermediate sizes, which
Isn't it true that near the Chicxulub crater, just on the crater boundaries are 60 millimeters, definitely nothing is there. But just above that in the dust, they have found evidence for the amino acids and things like that. Isn't it true?
Maybe. Better not to say because I'm not sure.
They found what?
Amino acids in the for example, the Danish side also, the system millimeters at this one, there you go. Near just the dust above, at the system millimeters, there is nothing, because you don't expect also to survive. But just above that, that is 62 millimeters, 60 millimeters kind of the dust, they have estimated the dust age from the depth. And they find that as a function of that, they do find the evidence for amino acids.
The uridium?
From they have done this one, iridium, but we are seeing the kind of amino acids have been seen, that's what I'm saying. In the Danish thing also they are, and then they are done it in the Italian, that and so like that. And in Chicxulub it has been really
But usually what they found is iridium content, they found
Yeah,
these minerals and some other, I'm not sure about amino acids and what they found. But that's the KT sort of ejecta discovery is more or less global.
Well, but there's a strong geographical dependence on in the Caribbean islands.
Which makes sense because it's concentrating more, it's decaying when you go away.
Yeah. And by the way, there has been found some remnants of the projectile in the Pacific. So some of it has been scattered out.
Okay, well, there aren't any more comments. We might close this session now and go for coffee, and we're 1:45. So we could take a half-hour break for coffee and 1:45.